So in this session, we would be looking into the other possibilities in the Z-plane. In addition to stability and causality, Z-plane works quite well for estimating the frequency response of a digital system, in which case it could also be called as a digital filter. So how one could measure the frequency response in the Z-plane is by making this a substitution given h of z, the transfer function. When we make the substitution z equal to e power j omega, then we get this simplified expression where it is h of e j omega. And as this h of e j omega is just a function of omega, we could further simplify and write it as h of omega. Okay, so h of omega is typically represented as the frequency response of the system. And you could see that h of omega is a complex variable. It comes from the fact h of z. Z is a complex variable, the Z-plane. And when we make z equal to e power j omega, it's a special case of Z transform, and in which case it becomes h omega. So basically, the frequency response of a digital system is a special case in the Z-plane where z equal to e power j omega. Okay, and given that it's a complex variable, we have both the magnitude and the phase, and the magnitude of the system is called the magnitude response, or people typically tend to refer this as a frequency response as well. Okay, so the words are interchangeably used. Essentially, h of omega provides an indication of how the digital system responds to different frequencies. Okay, so that's why it's called frequency response. And the phase of that is obviously called the phase response of the system. And phase response do play an important role. You have to watch out the phase response when designing digital filters to ensure it's not introducing what's called phase distortion. Okay, and we typically prefer the phase response of the system to be linear. Okay, when you plot the curve for the phase response, we expect the curve to be linear because a linear response typically doesn't introduce any distortion in the signal. Okay. So moving on, one possibilities with the frequency response is that a quick and an easy way to estimate the frequency response, we have looked into this h of omega before, is by using this notation here. So we know in the Z-plane, a Z-plane could be represented by using numerator and denominator polynomials. The roots of the numerator polynomial corresponds to the zeros in the system, and the roots of the denominator polynomial corresponds to the poles in the system. Okay, so when you have such a representation, then we could also estimate the frequency response by using this pole zero location. And this is, again, a very easy and a quick way to estimate the frequency response. And it's just given by the product of the distances of the zeros to the point omega on the unit circle divided by the product of the distance of the poles to the point omega on the unit circle. Very simple, high-level definition of getting the approximate frequency response of the system. So what it does is that it allows the user to get an idea whether the system we are dealing is a high-pass system or a low-pass or a band-pass or a band-stop system, just by using this formulation of the product of the distances of the zeros to the point omega on the unit circle divided by the product of the distance of the poles to the point omega on the unit circle. And remember, the unit circle is a special case, and it goes from 0 to 2 pi. So omega is nothing but 0 to 2 pi in a continuous way. But we are looking at a specific point omega on the unit circle at a particular frequency if we want to know. Okay, so this is basically getting a representation at one particular frequency. So it's h of omega. Omega is one particular value here, but theoretically omega goes from 0 to 2 pi. It's a continuous value, and we will also see how we are going to discretize that continuous value of 0 to 2 pi. So keeping that in mind, just going to show a very simple example of a system with a pair of zeros. Okay, as you know, zeros and poles appear in complex conjugate pairs. So here I'm showing a pair of zeros. One zero is right on the unit circle at omega s by 4, and by complex conjugation process, the another zero is at 3 by 4 of omega s. Okay, omega s is the sampling frequency of the system. Okay, so the unit circle, which goes from 0 to 2 pi, 0 to 2 pi, it basically covers 0 to omega s. Okay, omega s. So 0 to omega s corresponds to 0 to 2 pi speaking. So omega s is nothing but at the 2 pi location. Okay, so here it's a simple example of considering two zeros exactly on the unit circle, right at the point omega s by 4, and the complex conjugate of that would be at 3 by 4 omega s. So if we use the expression that's given for h of omega, the product of the distances of the zeros to the point omega on the unit circle divided by the product of the distance of the poles to the point omega on the unit circle. And in this specific example, there are no poles. So the denominator is 1. Okay, there are no poles, so the denominator is 1. So we just have the numerator. So we should just work out the numerator for this given simple example. And when we work out, and I'm trying to plot the magnitude response, and that's on the y-axis, and the scale omega is on the x-axis. So by using that thing, now when I start at 0 hertz, at this point, 0 hertz, the distance, there is some distance between 0 and the first location of the 0 is Z1. Let's call it Z1, and let's call this one as Z2. So this distance, whichever, let's call an arbitrary value, which is a scalar quantity, let's call it R. So it's at the distance of R. As we go, so at point 0, the magnitude of this one would be here, okay? As I go closer to omega s by 4, as I go closer to the omega s by 4, the distance is decreasing and it becomes 0 exactly at omega s by 4. So now the numerator has become 0. According to this expression, the numerator has become 0. And that's what exactly happening here. So as I go along the unit circle and I reach omega s by 4, it becomes 0. So the magnitude response has become 0. Now, when I start to go away from the unit circle, the distance is starting to increase. And obviously that's reflected here. As we go away from the unit circle, this distance is starting to increase because the location of the 0 is here. The distance is starting to increase. Okay. Now, what happens is that when we start to go closer to this second 0, okay, second 0, that's exactly what's happening. The distance between the point omega on the unit circle to this second 0 is decreasing. And when I plot that, it's going to 0 exactly at this location. And when I start to move away from here again, the distance starting to increase. Okay. So what you have seen here is a simple case of using this formulation that's been given here. All you need to know is that you need to know the location of the 0. Now, once you know the location of 0, now I'm going to go around the unit circle from 0 to 2 pi. When I'm going around the unit circle, initially at 0 hertz, we compute the distance between the 0 hertz and the location of your first 0, which is Z1, and we get that one value. So as we go along, we can essentially get a series of numbers, and when I just plot those numbers, it looks like this. So what has happened here is that the location of the two zeros, Z1 and Z2, the location of the two zeros has helped me to take out that particular frequency. Okay, so it's acting some kind of a band stop filter, or to be precise, it's acting like a notch filter. Okay, notch filter is one that removes a specific frequency from a given signal. Okay, so here I'm removing frequency which is omega s by 4 and 3 omega s by 4. Okay, so let's assume if the sampling frequency was 200 hertz, so I would be removing a 50 hertz, and I would be removing 200. Yeah, another one is at 1. So let me work out this thing. 3 times 200 hertz, which is the sampling frequency divided by 4. So this would be 50. And so I'm removing two frequencies, okay? This is 50 hertz and this one is 150 hertz, okay? If I assume the sampling frequency to be 200 hertz, okay? So it allows me to remove certain frequencies when we don't want it, okay? And for example, if you want to, in this specific example, if I wanted to remove something like a 25 hertz, let's say, so where would you place your zero? Okay, previously we placed the zero here and here. So if I want to remove exactly 25 hertz, I would place another zero between the 0 and omega s by 4 somewhere here. Okay, and by complex conjugation, I would have a mirror image of that here. Okay, so when I place these two new zeros, let's call Z3 and Z4. Now, by same formulation that we discussed before, if I go around that unit circle, here you will see a first dip in the frequency response happening at Z3 and second dip happening at Z1. And you go further, Z2 and another dip happening at Z3. So the location of this one would be Z3. Again, this is a h of omega, the magnitude response. This one, location of this one is Z1, which we have seen before. Location of that is Z2, and this location is Z4. From a frequency point of view, this would be 25 hertz, Z3 would be 25 hertz. We have already seen Z1 is 50 hertz, Z2 is 150 hertz, and Z4 would be 175 hertz. Okay. So now in this case, what's happening is that I'm removing 4 frequencies, okay, from a given signal. You got to imagine, in most of these cases, and if not all cases, this unit circle is basically a mirror image, okay? So whatever is happening in the second half of the plane is a mirror image, okay? So it's enough for you to just notice half of the spectrum, because the other one is just a mirror image of that, okay? So basically, in Fourier transform, any transform, as you know, we get both what's called the positive frequency and the negative frequencies, okay? So it's enough if you just look at one side of the spectrum. So if I just look at 0 to pi, then obviously this is what you would be seeing in your MATLAB and other things. So basically the given signal has 2 frequency components removed, one at 50 hertz and the other one at 25 hertz, okay? And by mirror image, obviously 150 hertz and 175 hertz are removed, okay? So this is a very simple way of just placing the zeros on the unit circle is allowing you to remove the frequencies that you do not want, okay? So if you know what frequencies you don't want to remove, then you can place zeros. Let's say if I wanted to remove all the frequencies that is between 0 to 50 hertz, okay? Then I would place a series of zeros on the unit circle like this, okay? Series of zeros, maybe 25 to 50 zeros around the unit circle as tightly spaced as possible. So with this example, what will happen is that it will remove this particular configuration will remove any frequencies that is between 0 to omega s by 4, which in case it's 50 hertz. So it will be like this. The plot would be something like this, where this is 50 hertz, okay? So essentially what this has become is that it's trying to remove any frequencies that below 50 hertz and passing any frequency above 50 hertz up to 100 hertz, because this is omega s by 4. Now, this kind of a filter, as you could imagine, is that when it's not allowing the low frequencies to go through and it's allowing the high frequencies to pass through, it's called a high pass filter. So a high pass filter design would look something like that, where I would place all zeros in the frequencies that I don't want to pass, and I would just leave the second part empty without any zeros, so it will pass all those frequencies. Okay? So getting an idea about just how by placing zeros, you can design different filter configuration. Obviously, it's not an optimal design because it's, as I indicated, it's just an approximation on a high level concept. And here, I mean, I just said we can place 25 to 50 zeros for the simple high pass filter example. But again, we don't know how much we should go for. What's the optimal number of zeros we need to place? I mean, theoretically speaking, we should place infinite number of zeros between 0 to omega s by 4 or 0 to 50 hertz, so we can remove all the frequencies as tightly spaced as possible, so nothing passes through the system. But that's not practically feasible to have infinite number of zeros, okay? But it just gives an idea that, you know, zeros helps to attenuate or remove a certain frequency, okay? And it has to be on the unit circle. Now, if you look into this expression, which is what helped us to uh, get the plots, now the poles are in the denominator. Okay, the poles are in the denominator. Okay. Now the same concept applies. Let's assume that we don't have any zeros in the system, which means the numerator would be 1 and the denominator will have poles, for example. Okay, so let's assume if you have 2 poles, it basically says at the point of omega when you have poles, the distance becomes 0 at that exact point, and 1 over 0 will blow up the system. It will make the frequency go very high. Okay, because 1 over 0 is infinity, it will enhance that particular frequency very high. So the poles are playing the opposite effect. It enhances the frequency that you wanted like that, whereas zeros are suppressing the frequencies that we have seen before, and the poles are allowing to enhance the frequency. And this is, again, not possible practically because we cannot have pole exactly on the unit circle because it's infinity and it leads to instability in the system. Okay. So what people do is that if you want to enhance a certain frequency, you don't place the pole exactly on the unit circle, you just place it slightly below the unit circle. Okay, so somewhere here, like a distance of 0.9999. Okay, because you know 1, the magnitude 1 would be on the unit circle, but if I have 0.999, it's very close to the unit circle. It's not exactly on the unit circle, and this will make sure that the denominator doesn't go to 0. It's almost a very small value, and it's still stable, and I can definitely enhance that particular frequency because that's in the denominator. Okay. So the placement of poles and zeros allows you to suppress or reject a frequency with the zeros. And if you want to enhance the frequency, you can basically use poles. Okay. So very interesting concept, and it plays a very significant role because pretty much anything we see in a signal spectrum could be seen from a pole zero point of view, because obviously when you have peaks and valleys in a spectrum, that basically corresponds to the frequency spectrum of any given process. Okay, and from your earlier concepts, you know that whenever there's a frequency enhancement, like what we have seen here, the frequency enhancement, this could also be seen as a resonance. Okay, so when I'm speaking now, when I say vowels like A, E, I, O, U, for example, they all tend to produce speech signals with resonance, and they tend to have these peaks during wherever there is what's called formant frequencies. Okay, and basically, naturally, what we do is in biomedical processes that we tend to enhance certain frequencies because of the inherent physiological aspects of it. The same thing applies in heart sounds. Same thing applies in other biomedical signals. When a certain part of the spectrum gets enhanced, that's because it's essentially coming from the location of the poles in the system. Okay. So here you see I'm trying to mimic the natural physiological concept with the idea of poles and zeros. This will get much more clearer as we go by, but the idea is pretty simple. Just by remembering this concept of the product of the distance of zeros to the point omega on the unit circle divided by the product of the distances of the poles to the point omega on the unit circle will give us fairly a good idea about the magnitude response, or in other words, the frequency response of a given system. Okay. The reason we are putting distances of the zeros is that the examples we took is just one pair of zeros or one pair of poles, but in practical filters and in practical systems, we have multiple zeros and multiple poles. Okay, that determines what's called the order of the system. Okay, so that's why you got to keep in mind it's product of the distances of the zeros, and the product of the distance of the poles is a plural concept here. Okay. Okay, so with this in mind, what was shown was just as indicated, very approximate to know the frequency response, approximate to know frequency response. It's okay to use the word interchangeably. Magnitude response, frequency, they both mean the same. Basically here what we are saying is that we are not giving much emphasis on phase response, and most of the signal processing could be done just by looking into the magnitude response. The phase response, as long as it's linear phase, people don't bother to look into that further. Okay, so an approximate way to know frequency response is through the pole zero placement. Okay, so this is where we have gone one step further. Okay, previously we saw how the poles and the zeros can determine the stability and the causality of the system. Now we have seen how the poles and zeros can play a role in determining the frequency response of the system. Okay, so it's a powerful tool. I mean, even if you didn't have an exposure to Fourier transform properties, if you didn't know how to compute the spectrum of a signal, just from a Z transform point of view, you can get an idea of that also. Okay, now let's look into a formal ways of defining the frequency response, and now we are entering the territory where we are starting to design digital systems, or in other words called digital filters. Okay? Digital filters allows you to pass certain frequencies, suppress certain frequencies. So here we will see a few formal ways of doing it. And filter response, just going back to the earlier concept of this block diagram that we have seen a few times before. And input X goes into the system H, and you get Y, is exactly it. So here we are trying to design your H so that it will modify my X in a way that I wanted my Y to appear. Okay, so if you wanted to remove, for example, 60 Hertz interference from your X signal, then I would be designing my system H, in other words, filter H, to remove that 60 Hertz interference. So the output Y would be free of 60 Hertz interference, and that could be expanded to any other concept here. Okay, so essentially, the filter design, which we have seen before, is nothing but finding out your H. The time domain H, as you know, is called impulse response, and in the frequency domain H is called transfer function of the system, okay, or the filter. So you have the same concept seen as impulse response, a transfer function. And when we make a very special case of the transfer function Z equal to e power j omega, it becomes the frequency response of the system. Okay, so they all are interconnected. So in other words, H, we have seen H of Z, we are familiar with that. Now we know H of omega is a special case of that. They all mean the same. They're all interchangeable. Okay, so this is exactly we are getting into. We are getting into how do we find out this H, in a much more systematic way. Okay. Now it happens that in certain cases, the value of H, I'm talking in the time domain, okay, I'm talking in the time domain, H will have finite values. Okay, the impulse response would have finite number, maybe 10 values. Okay, when H has 10 values, as I indicated in the course, normally we see these things as vectors. So if it's a length of 1 by 10, 10 numbers H, then it's called a finite impulse response system. Okay, FIR. FIR is one which has finite impulse response. The infinite response is finite. Okay. On the other hand, finite impulse response. On the other hand, you can imagine when I wanted to do the transfer function of this FIR system, H of Z equal to will become H of Z is nothing but, as you know, it's nothing but the Y of Z by X of Z. Okay. So in this case, the finite impulse response, if you work out, when you have a finite values of H of n in the time domain, H of Z will only have zeros in the system. Okay? So an FIR system does not have poles in the system. It's only made up of zeros in the system. Okay, it's important because it doesn't have poles, so we don't have to really worry about stability of the system anymore here. Okay? FIR systems are inherently stable systems. Okay, because it's made up of all zeros. Okay? And the only thing is that we have seen when you have only zeros in the system, it helps you to suppress frequencies. On the other hand, if I wanted to have a sharper cutoff, or if I want to enhance a certain frequency, we need to have poles in the system. Okay, so when you do want to have poles in the system, then from a filter point of view, we start to call those filters as IIR filters. Okay, as the name indicates, is infinite impulse response filters. Okay? Impulse response. Essentially, there are two forms of digital filters, FIR filters and IIR filters. Finite impulse response filters, as the name indicates, has a finite number of values in its impulse response, which is in the time domain, H of n, by the way. Okay? Whereas infinite impulse response has infinite values of H. So it's not practically realizable, and we will see how do we really realize IIR filter by having finite number of values, okay? And by definition also IIR filters as poles in the system, which means there is a denominator polynomial, and FIR systems on the other hand only have zeros in the system, okay? So let's just now focus on designing an FIR filter first, finite impulse response filter. Then immediately we will jump into the concept of designing infinite impulse response in a practical way, okay? So the first approach is of designing FIR filters by using a very well-known methodology called a window method or windowing method, okay? So what happens here is that we go through two steps basically. So once you wanted to design a filter, let's say you want to design a low-pass filter, you would be picking the low-pass filter's ideal impulse response of that low-pass filter. Then ideal impulse response, we will realize very quickly, is not a finite duration. Okay, ideal. If you want an ideal impulse response for any given filter, for example, low-pass filter, those values doesn't end to be finite. So if it's not finite, it's not an FIR filter. So how do we make it finite? We need to do some kind of a truncation. So the truncation is the key part here by using a window function. Okay? So some of these concepts of window function now might ring a bell for you from your earlier courses. So the window function now is coming in quite handy in designing a practical FIR system, okay? Practical FIR system. So we will see some examples to make the concepts clear. And there are many window functions you could use, but the commonly used window functions in designing FIR filters are Hamming, Hanning window, rectangular window, and Blackman window. Okay, so each window has its own special characteristics, but more or less it's either the window is a sharp window or a smooth window. Okay, like a rectangular window is considered to be a sharp window, whereas you take Hamming and Hanning windows, they're considered to be much more smoother window functions. Okay, and window is nothing but it's a time domain function. It's just a time domain function. You will see very soon how a Hamming window looks like. So if that's a case, now how do we know the ideal impulse response? Okay, let's assume I want to design in an ideal low-pass filter, in the frequency domain. Let's call omega domain. This is an ideal low-pass filter with a cutoff of omega c. Okay, and this is h of omega on the y-axis, the magnitude. Okay, and I could also use the variable f, as you know. 2 pi f is nothing but omega. So sometimes we use the thing interchangeably. So f and omega could be interchangeably used. And just to make it clear, your omega is nothing but 2 pi f. Okay, just one is angular frequency, the other one is the straightforward definition of frequency, which is f variable here. Okay, so if I want an ideal low-pass filter, this is an ideal low-pass filter. So what happens is that if any frequency is above omega c, the system doesn't pass it. It only passes frequency from 0 hertz, which is DC value, to omega c hertz. Okay, so this is an ideal low-pass filter. Now, how would this ideal low-pass filter, as you know, this ideal low-pass filter has been in the frequency domain, but how do we get the ideal low-pass in the time domain, which is nothing but the impulse response? So exactly what I have given you here is that the different filter types and their ideal impulse response. And so this would be an ideal impulse response of a low-pass filter. So this is exactly in the frequency domain which we plotted. You know that either the Fourier or the inverse Fourier transform of a rectangular function is a sinc function. Okay, so this rectangular function would start to behave like a sinc function in the time domain, in the h of n domain. Okay, by using the inverse Fourier transform, because I need to go from omega to the time domain. So I'm using inverse Fourier transform to do that. And the same thing applies. The forward Fourier transform of a rectangular function is also a sinc function. Okay, so that's what's happening. So in an ideal low-pass filter, we'll have 2fc sine n omega c by n omega c. Okay, whenever n is not equal to 0, but when n equal to 0, we just have to make sure it's 2fc. I mean, it's pretty obvious. Even when you substitute n equal to 0 here, you'll get the same expression. But just I need to make it clear that we are dealing with a function which is like a sinc function. Similarly, we could have ideal impulse response of other filters like high pass, band pass, and band stop. In all those cases, an ideal high pass filter is something like this. It passes any frequency that's above omega c. in the frequency domain. A band pass filter would be passing any frequencies that is between two frequencies. In this case, it could be omega 1 and omega 2. That's an ideal band pass filter. And a band stop filter is essentially going to stop any frequency that's between the two bands that we don't need. Okay, so this would be an example of an ideal band stop filter. Okay, and in many cases, a notch filter, which removes one particular frequency rather than a band of frequency, is a special case of band stop filter. Okay, the reason I have to point out notch filter is that it's very much needed in biomedical context, because pretty much all biomedical instrumentation goes through this power line interference, and power line interference is a dominant factor, 60 hertz. Whenever we have our lights on or any electronic equipment is on, the 60 hertz hum gets into our physiological signals and might mislead the interpretation. So you have to make sure that 60 hertz noise is filtered out. Okay. And power line in other countries are 50 hertz. So depending on which country we are talking, either we have to remove 50 hertz or 60 hertz. But in North America, it's 60 hertz. So in fact, in your lab 2, you would be removing a 60 hertz interference from an ECG signal. So that's a very important pre-processing step. And again, as indicated, in many of the physiological signals, a frequency around that 60 hertz tends to have a very significant clinical value. So if we don't do the notch filtering, then you might be getting a wrong interpretation of the results. Okay, so that's why notch filter is a special case of band stop filter. So this is an ideal high pass filter, HPF. This is an ideal band pass filter. This is an ideal band stop filter. So in all those cases, they tend to have an ideal impulse response, which has some kind of a sin x over x behavior, like a sync behavior, okay, in the time domain. Okay. So I've just summarized these mathematical expressions because in this course, you don't have to really know about how to go about in doing the Fourier transform or the inverse Fourier transform to get those values. I am assuming you have an idea, a concept, and you don't have to even memorize these mathematical expressions of it. Okay, if at all needed, it will be provided to you. But the whole idea is to just to give a feeling that, you know, mostly we are dealing with box type functions, like this is a box function. And this could be also seen as some kind of a box function. So whenever you have a box or a rectangular type function in the other domain, either in the time domain or the frequency domain, it tends to have the sync behavior, okay, sin x over x behavior. Okay, so this is basically the ideal configuration when you want to design ideal filter. When I say ideal filter, is that when you want to remove certain frequency, the cutoff is very, very sharp. Okay, so that's probably the definition of an ideal filter is that. So here omega c, this cutoff is sharp. In other words, no frequencies even slightly before omega c would be passed through the system. They all get filtered. The same applies here. Sharp cutoff, sharp cutoff. Okay, so this is where it gets interesting because we are looking at sharp cutoff, and sharp cutoff is very, very difficult to get. Okay, very, very difficult to get in practice. Okay, let's say if you talk about analog filters, now we are talking digital filters, and you will see what basically digital filters means in a hardware level. We will get to the point. Okay, digital filters have a hardware realization. In hardware, how do they look like? Okay, the equivalent of digital filters is analog filters. When we don't do digitization, you can even build an analog filter using op-amp circuits, RLC circuits. So you might start to design an ideal low-pass filter today, but with analog circuits, what happens during over time is that these values get influenced by the external temperature changes, humidity, and all those factors. So your RLC values might deviate from your original design. So when your RLC values start to deviate, then this cutoff which you designed will start to also change. Okay, it will start to deviate. So that's why analog filters are really not that good in providing sharp cutoffs. Digital filters tend to have some stability in giving sharp cutoff, but there are certain cases where we might have to compromise that, and we will get to that point pretty soon. Okay, there are very few applications, by the way, in biomedical so far where we know we need to have sharper cutoff. For example, if you want to do Eeg spectral analysis, and we have seen that before, for example, if you wanted to analyze alpha waves and beta waves, alpha waves goes from 8 to 13 hertz in the Eeg. So you need to use a very sharp cutoff to get the 8 to 13 hertz frequency bandwidth. And if you want to get the beta waves, it goes from 13 to 30 hertz. And again, you need to have a sharp cutoff for those bandwidth requirements. Otherwise, you are looking into wrong alpha rhythm or wrong beta rhythm. Okay, so that's just a very small example to know why a sharp cutoff is needed in some applications in biomedical field. Okay, so keep this in mind. So the example I'm going to show to you is basically going to be a low-pass filter design, an FIR low-pass filter design using the ideas we have just seen. Okay, so here the requirement for the filter design is that you are asked to find the impulse response of the FIR filter, a low-pass filter. An impulse response is a time domain variable, so it's pretty obvious. I need to find what's my H, okay, or H of n to be more specific, impulse response of the system. And to meet the specification, the cutoff frequency is given as 1.5 kilohertz. The transition width is given as 0.5 kilohertz. And the attenuation in the stop band should be greater than 50 dB. And in any digital system, we need to know the sampling frequency. That's the number one requirement. Okay, so here the sampling frequency is given as 8 kilohertz. Now, how does this requirement looks like in the form of a diagram? Okay, in the form of a diagram, this one looks like, okay, so we have the x-axis, which is a frequency. So if you allow me, I will switch to F to be more easy to understand. We can also use omega F. So here I'm requesting the low-pass filter to have a cutoff of 1.5 kilohertz. So the FC is 1.5 kilohertz. Okay, it's a cutoff. And there's a transition width of 0.5. Okay, so this gives an idea. This filter is not going to have a sharp cutoff. It's going to have something like this. Okay, so this one would be your FC. And this transition width that I'm talking here this transition width is going to be 0.5 kilohertz. Okay, it may not be to the scale, but I just want you to understand this is what exactly I'm talking. Okay, the transition 0.5 kilohertz. And what happens is that the attenuation, the stop band attenuation I'm talking should be greater than 50 dB. So this attenuation that we are talking here, the attenuation is after the cutoff. The roll-off rate should be greater than 50 dB. Okay, so that's another requirement of it. Okay, so in an ideal case, obviously, in an ideal case of this low-pass filter, the design would have been, the cutoff would have been like this sharp cutoff. Okay, that's it, like this red line. But the blue line is what the design parameters telling that, okay, we know we cannot get a sharp cutoff, and we will understand very soon why. So I'm allowing you to have a roll off that not exactly at 1.5 kilohertz, you can roll off a little bit with the transition width of 0.5 kilohertz. Okay, and with this parameter being given to you, now we have to just go through the process of design of this FIR filter by just using the block diagram that we just saw. So if you see this block diagram, we have the ideal filter response. Now you want to truncate using a window to get the practical FIR system. Now the truncation is becoming the key point here. Truncation is becoming the key point here. Okay, so going one step further for this given example, if I go through the same thing which I just discussed, ideal low-pass filter, we have seen the expression of the ideal low-pass filter to be 2fc sine n omega c by n omega c when n not equal to 0, n equal to, it's just 2fc. Okay, pretty obvious. Now this function is having the role of sine x by x. Okay, and the definition of that one is sinc x. Okay, sinc x, and the sinc function looks like this. Okay, so this is what, so the ideal low-pass filter is 2fc of sinc function, and sinc function, the tail keeps wagging, the tail doesn't stop. This guy, the tails of this one keeps going up to infinity. Okay, there is small values up to infinity. Okay, so what is happening in ideal low-pass filter has actually infinite values because the sinc function doesn't reach 0 even when it's infinity. That's a property. It might have a very, 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 very small value, but theoretically it's not getting to 0 value. So what's happening with this ideal low pass filter is basically an infinite values. So it's an IIR filter, an ideal low pass filter. This is very, but I need to design a finite impulse response filter. Okay. So how do I make this one finite? Is that you need to truncate with the window, a very simple concept, okay? You need to truncate with the window function, and the window function, truncation could happen many ways. I could just truncate by using a rectangular function, just take these values, or I could take another rectangular function. I can take a longer rectangular function, take these values. So in all these cases, what's happening is that it's just the finite impulse response filter length. This is the length of the filter, number of values I need changes, okay? So if I have infinite values, it's infinite impulse response filter, but I can always have a larger values, larger filter length. It's all good. But issue with the larger filter length is that when you have a larger filter length, we will realize it will introduce delay. So if you're trying to process signals in real time, for example, you wanted to control a wheelchair by using your brain waves, you cannot have a lot of latency or delay in the system. The delay or latency comes because of the filter length. Longer the filter length, longer the delay would be. And we will exactly come to know why that is causing delay. So it's always good to have a shorter filter length. So here I can truncate in two ways. I can truncate like using a rectangular function like just I showed you, or I can take a longer window, or I can take any other window, okay? It's up to you to select the length of the window function. But here I have to be very careful in selecting the length of the window function because it has to match my specifications given by the design criteria, okay? It has to match these aspects of it. So this is going to determine what should be the length of the window function. And very soon we will see it is nicely given by a formula, okay? Now I could select any window function I want to truncate, but the example I showed with the green was a rectangular window function. In other words, I'm using a sharp window function, but nothing stops me from using other window function. Like I could use a Hamming window function, which would be taking this infinite impulse response and multiplying with a function like this, a smoother window rather than a sharp window, okay? Now you got to remember, when I'm doing a multiplication, okay, now I'm multiplying this sharper window with the ideal impulse response. Multiplication process is happening in the time domain. Anything we doing something in one domain, one form of operation will have an impact in the other domain, and we know that. So multiplication in the time domain will lead to convolution in the frequency domain. Okay? So it's not that, you know, I'm not spoiling anything in the signal. Yes, I would have used a rectangular window or a Hamming window. It does mean I am impacting the signal's spectrum. Okay? So if we didn't use any of the window function, this function by itself would have given me an ideal low pass filter. But again, we know it's of infinite values, so I got to truncate. When I truncate the values, this ideal thing, because of this truncation process, which is a multiplication process in the time domain and leads to a convolution process in the frequency domain, will not give me exact sharp cutoff. It gives me like filter responses like that, okay? Just as few examples. So it does have this roll-off that's coming naturally because of the windowing process, but we have to make sure that roll-off or the transition that's happening is controllable, okay? So you could select any window function, but for the example, I'm selecting a Hamming window function. And with the Hamming window function, which we will see here, it looks like this. It's in other words, the ideal impulse response is now going to be multiplied by this Hamming window function, which as I just indicated, is a smoother window function, okay? Now, by using the specification, we were given a transition width, okay? Now I need to, when you given the sampling frequency, because once you take it to the computer, or even you would have realized when you take it to the MATLAB, there it just becomes a bunch of numbers, okay? Now, how do we give a context that these are signals which are sampled? Is by using sampling frequency. So that's why in the design formula requirement, the sampling frequency was given as 8 kilohertz, okay? So if that's the case, I need to make sure I use the sampling frequency to ensure my filter is taking account of the sampling frequency, and they all get what's called normalized. So normalization is a very simple process. So I was given the transition width, as you know, transition width was given as 0.5 kilohertz is a transition width that I need to accept. Now also the sampling frequency was given as 8 kilohertz. So all I'm doing is that the transition width is now normalized, okay? So I've divided 0.5 by 8 to give this normalized value. So now this is what computers understand. Computers understand this, and the sampling frequency knowledge is indirectly incorporated because I've normalized with respect to the sampling frequency here. Okay, so the normalization is the key part, and that's why you need to use the value fs, or the sampling frequency. Okay, now it's been known that transition width, which is what the roll-off that I was talking, can change according to the window function I'm selecting. It becomes property of the window function. So if I had a rectangular window function as opposed to Hamming, then the transition would be different. If I had a Hanning window, the transition would be different, and so forth. But it's known, and these formulas will be given to you, and you don't have to derive that. The transition width for a Hamming window in a normalized way is given as 3.3 divided by n, where n is the length of the number of coefficients I need to take, or the filter length. Okay, 3.3 by n. Okay, so by using that concept of 3.3 by n, now if I just plug in the transition width, which is delta f, n becomes 3.3 by delta f, just reversing the formula here. When I do this, now I got the number 53. What is this 53 telling me? 53 is telling me all I need to take from that impulse response, ideal impulse response, which has infinite value, I need to take only 53 samples out of it. Okay, so this is exactly that we are getting at, because that's again derived through the transition width. In other words, I am telling me just give me 53 values from this ideal impulse. 53 values is good enough for me to satisfy the design specifications that has been provided to you, okay, by using a Hamming window. Okay, 53 values. So that's exactly, now what has happened is that infinite impulse values, which are infinite values, have been now truncated into 53 finite values. So this is your FIR filter length, they call it, or the length of the impulse response. It's also called filter order. So the order of this filter is 53, and that's coming out because I can only take certain number of values from the impulse response, ideal impulse response, because ideal impulse response is infinite. I need to take 53 of that, and that's coming from this very simple value here. Now, how do we determine each of those coefficients that we just talked about? How do we determine 53 coefficients that I'm picking up? It goes back to the original calculation. This is the ideal impulse response that we had. This is a Hamming windows function. I'm just multiplying it, and I'm taking 53 values, which is symmetrical around the origins, the 26 values on the positive side, another 26 values on the left-hand side, and including n equal to 0, you have 53 values. Okay, so if I go back, it's nothing but if I have the impulse response, which was like this, 53 values, in other words, 26 values on this side, and other 26 values on the other side. Okay, and there's one at n equal to 0, so 53 of those values I'm getting. So it's obvious, all you need to compute is the 26 values, because the other half is symmetrical. Okay, the impulse response, because the ideal impulse response of a low-pass filter is symmetrical because of the sinc function property. Then it's enough if you compute one half of the other half is symmetrical. Okay, so when we do this calculation, when I got those 53 values, it means I have designed a practical FIR filter, and by going through the steps of that, and just ensuring that there are certain simple things we need to take care. The Hamming window function mathematically is given by this notation. Again, these things will be given to you. You don't have to remember. You see the Hamming window function, which I just plotted before, which was looking like this as a behavior based on a cost function. So it's much more smoother as compared to a rectangular function. Now, because of the transition width that I'm using, it's very hard to get the cutoff frequency exactly at FC. Okay? The cutoff frequency. So you got to keep that in mind, because it's not a sharp cutoff. So the variance that's allowed with the Hamming window, with the cutoff, is that the new cutoff could be FC prime, and that's again coming from that transition width by 2. This is the original cutoff that was given. Transition width by 2 is the allowance that I could give, and it's just a design consideration. If you want the allowance to be much more bigger, then you can always change this value. But here I'm assuming delta f by 2 as a choice here, and divided by the sampling frequency, because I need to divide anything by the sampling to normalize those values. When I do this one, the new cutoff is something like that. So it's not very far away from the original cutoff. It's incorporating the transition width that's required by the design criteria. Okay. So this filter, which practical FIR filter with 53 coefficients, will be designed for a cutoff of FC prime. Okay, and it's not going to be far away from my original FC that was given. Okay. If you don't want this, you can always design with FC in mind. it doesn't hurt you, but by doing the FC prime, you are aware of the fact that your window is not a sharp window. In other words, you don't get a sharp cutoff. You're allowing this roll-off as a design consideration. Okay. So with that being going on, we have to compute the actual FIR coefficients. It's easy. Now I know the mathematical expression for my ideal low-pass filter, the mathematical expression for W. So all we need to do is that use this HDN omega WN, sorry, not omega, it's WN formulation that we just talked throughout and substitute for n equal to different values. N goes from minus 26 to plus 26 values. So when I plug in n values into it, I start to get the filter coefficients. Very straightforward, and that's what's happening here. And n equal to 0, at the 0th thing, my filter coefficients 0.4375 value. When n equal to 1, I plug in into that expression just I showed you for both ideal low pass HD and the value for the Hamming window. Then we get h of 1. By symmetry, h of 1 is nothing but h of minus 1. So I get the other coefficients also. So I got those values, numbers again. We can just continue on. It's pretty straightforward process. When n equal to 2, you go through that, you get these values. So likewise, okay, this is h of 2, h of 1. Likewise, you can proceed, and h of 26 will be this, okay, minus 10. So you get 53 of those values. So you get 53 of those values. So one value, two value, the third number, like that you will get 26 of those numbers and symmetry. So you get 53 values in total. So if you see these 53 values are my filter coefficients, FIR filter coefficients, which is going to cut off any frequencies that is above 1.5 kilohertz, and is going to give me the stop band attenuation I need. And it's a practical way of designing the filters in a much more formal approach. Okay. Now, thing you need to keep in mind in this filter design problem is that when you see the filter coefficients, the values, you see 0.4375, 0.3119, these numbers are very, very important. Okay, most of these numbers tend to have very large floating point values or tend to have double precision values. So you cannot really truncate these things. When you truncate even 0.00913 to, for example, to 0.001, you are introducing artifact, because these numbers are very sensitive in the filter design, and you're going to introduce artifact which will give you a different cutoff than what you originally designed with. Okay? So in a digital filter design, just like how we talked about analog filter design, analog with RLC circuit, the RLC values, the resistor, inductor, and capacitor values could change with temperature and humidity. In a digital filter values, the values numbers don't get changed unless you represent the numbers by using some truncation process. Okay, so these numbers should be floating point. It should be represented as it is in the computer without any truncation, or it should be represented as it is in the microcontroller or microprocessor. The moment I do some approximation to the numbers, then I'm getting a wrong cutoff. Okay, so that's the only way your digital filter could change the value from the original design is in the implementation. So number implementation there. So in digital filters, a key criteria is the number representation. Okay, it's good to keep the number as it is, what you get from your mathematical design, and don't do anything to the number. And when you're dealing with these floating point numbers, you can imagine they are all eventually represented in the computer using binary representation bits. So this is where we talk about microprocessor and microcontrollers of different processor length. We call 8-bit microprocessor, 12-bit microprocessor, 16-bit micro. Basically, it says the higher the number of bits in the microprocessor or in your CPU and GPU, it means a very good representation I can have of those numbers, which means whatever you design will have a very sharp cutoff and the cutoff that you're looking for. Okay, so this comes back to the hardware representation of that, and we will get to know more of this. What does the digital filter looks in hardware? It's very simple, a digital filtering process. So once I got this number H, as you know, H I have obtained. This is a vector of length 53. For vector, let me use the notation underscore. It's of length 53. So these 53 values would be now programmed into your computer or microcontroller. Now, any signal X that's going into this filter, signal X is nothing but a vector going into the thing. will go through a low pass filtering of 1.5 kilohertz, and output Y would be a filtered version of that. Okay? So it's basically becoming what output Y is doing is, or how we got that is a convolution of H with X, because it's a linear time invariant filter. That's exactly what we're doing. So these numbers, 53 numbers, will be convolved with your input X to get the output Y. So in a practical implementation, it's convolution. So convolution is nothing but multiplication and addition operation, repeated multiple addition operation. So a digital filter is something that has multipliers and adders. That's all. Okay? So you have known from your analog filters, RLC circuits, and op-amps. Here, digital filters are one that is made up of multipliers and adders, and we will also see a third element, which is called the delay element, delay flip-flop, delay element, because you need to delay the input variables, because in convolution expression, it's not that x of n gets multiplied by h of 1, it's also x of n minus 1. You need to do the shift, multiply, and add. Okay, that's how the convolution expression. In other words, let me give that to you. It's nothing but this expression h of k, x of n minus k. So there's also this delay operation. Obviously, there's a multiplication, and the summation is allowing it to add it. Okay, so all those three operators form what's called a digital filter. Okay, okay. So very simple explanation for the filtering concept in the digital domain. Okay, so with that being said, so this example was just to show how you could design a finite impulse response system by using a windowing method. Okay, windowing method. And let's say if you are just asked to design a high pass filter similar to what we designed, the low pass filter and high pass filter with a similar cutoff of FC, and I will go back into the original notations we gave you. So this is a low pass filter, ideal low pass filter, and an ideal high pass filter is minus 2 FC. The minus is hidden here. Minus 2 FC sine n omega c by 1. That's a ideal impulse response of a high pass filter. So essentially what becomes is that once you design a low pass filter, if I wanted to convert the same low pass filter to behave like an high pass filter, for example, this example, then you don't have to worry much. You got these filter coefficients, the 53 coefficients with you now. All you have to do is that you flip the alternate values magnitude or the amplitude values. Okay, just to flip the alternate values. In this case, okay, this one will remain the same. H1 will become negative 0.3119. H2 will remain the same. H3 will get the negative of whatever we got. So you just say change the signs of the alternate values, and just this expression, if you just do this expression on the coefficients or the numbers you got with the low pass design by using minus 1 to the power of n, then you get the high pass filter coefficients. Okay. So it's very simple. Just going from a low pass to a high pass in this process is just flipping the values of the alternate signs. Okay. So that's a good thing. I mean, with these numbers, the number theory concepts, all those things are easily addressable. Okay, so here it becomes, we could get a high pass filter with a cutoff of 1.5 kilohertz by flipping the alternate values that we get with the low pass filters 53 coefficients. Flipping the alternate values will give me the impulse response of a high pass filter. And in the magnitude response is very clear. It's other half of what is going to be passed in the system. So instead of cutting off any frequencies above omega c, I'm going to pass any frequency above omega c. So in the frequency response domain, it's just the low pass and high pass are connected through this expression. Okay, and again, there's no expectation for you to derive these values. Okay, I mean, this formula will be provided to you. The whole idea is to just get the concept here going. Okay, so with this thing in mind, you would be looking into some filtering applications in your lab assignments, and whatever we talked here is easily you can take it to MATLAB, and you can easily take into any hardware description language like in Verilog, and you can make hardware circuits also from just the same concept I have told you. Okay, so there are also software tools available to provide this filter coefficients automatically for you. Just as I indicated before, you got to keep in mind that the sensitivity of those numbers with the filter coefficients has to be highly secured. because you can't really afford to change or approximate these number values, which are typically floating point number values with high precision. Okay, so that's the key part that you got to keep in mind. Okay. So with that, we will stop at this point and proceed into the other filter design problems pretty soon.